So let's start again. The next speaker is Nenna, who is going to present our joint work. He is at Paris-Saclay, and he's going to talk about optimal transport, entropic, and grand canonical ensemble, which should please all the physicists in the room.
So just give me a minute, okay? So everyone can hear me in the chat. So just to be sure that I'm not switching off the mic. It's okay. So thank you again for the invitation. It's quite a pleasure to be a conference in person after almost 2 years from the last one. So I'm going to talk about this work. It took us almost 4 years to do it, especially because probably I'm quite lazy. And the paper, I think, that will be soon available on archive, also depending on me, I think. And this is a joint work with Simone Di Marino and Matteo Levin. By the way, just an advertisement for Matteo. He will be a speaker at the next ICM the next year. So if you want to attend an amazing talk by Matteo, just go to Russia next summer. So I will talk about this grand canonical optimal transport, but before. So since it's almost time for lunch, I just have 16 slides, so don't worry, it will be probably fast. So first of all, I will introduce you, I will remind you some stuff on canonical optimal transportation, so just a standard optimal transport, and especially multi-marginal optimal transport, and maybe our main motivation, which comes from the electron-electron repulsion, so from quantum chemistry. And then I will try to motivate that's a good idea to introduce this generalization of optimal transport on the grand canonical ensemble. And if there are some physicists in the room or in the chat, maybe they already know what grand canonical ensemble it is. So it means that you have a system, and this system is exchanging particles with the external world. So it means that now you do not know exactly how many particles you have in your set. And then, of course, since this is workshop on optimal transport, but also on Schrödinger, we must have some Schrödinger in the room, and so I will extending Schrödinger. I will extend Schrödinger problem to the case of grand canonical ensemble, which, by the way, was in some sense already done in the early 80s by Lieb. An amazing problem on inverse problem density functional theory. So let's start with the canonical optimal transport, and especially with multi-marginal optimal transport. So most of us are used to classical optimal transport, where you just have two measures. But in this case, we have n measures, okay? And then, of course, what you are looking for now is actually to minimize an energy. So this E, and you have a given cost among all probability measure P, which have mu1, mu(n) as marginals. So you see that now you are working with a much bigger object than in the usual optimal transport problem. And let's say that, of course, since I'm trying to give you the point of view of a physicist on optimal transport, I will always talk about minimizing an energy. So you know that when you have the quadratic cost, you are minimizing an average kinetic energy. So you can also reset the dynamic, the Lagrangian view of quadratic optimal transport as a multi-marginal optimal transport by discretizing this probability on the path in time, and so you can still minimize the kinetic energy. And I will soon, since I'm going to talk about electron repulsion, you can imagine that this potential will be the Coulomb potential, and so I will minimize the average electron-electron repulsion. And of course, you know that when you do optimal transport, one of the first questions that you ask yourself is that you have a solution à la Monge. So it means that your P is deterministic, or in another sense, it means that the support of P is concentrated on the graph of an optimal transport map. So in this case, just fix, for example, mu1 as your reference measure. You want to see if there exists n-1 optimal transport maps such that Ti push forward mu1 onto mu I. And of course, the first one is the identity, because trivially mu1 is transported on itself. So actually, this when you just had a marginal, the problem actually became quite difficult to treat. And so we have this nice example with Simone and Augusto that we did some years ago. So you are in one dimension. So usually in one dimension, you know that everything works. Well, it should work. You have just one more marginal, and all the marginal are equal to the uniform, to the Lebesgue measure on 0, 1. And moreover, look at the cost. The cost is something nice. It's just the square of the sum. So it's convex. You think that you are in a nice case, and what happens is that no, it's wrong, because you have that uniqueness of your transport maps fails, and moreover, you have these weird maps which we decide to call fractal maps, and they are not differential at any point. So you see that these actually change everything from the two marginal case. You are just in one dimension, you had one marginal, you have a nice cost, and still everything goes in the wrong way. But why multi-marginal problem is so important? Because there are some nice applications. So one of the most known one is probably the Wasserstein-Barycenter problem. Of course, the Wasserstein-Barycenter problem, you can formulate it as the minimization of a sum of W2 distances, but still you can reformulate it as a multi-marginal problem. And so, I mean, this is a nice formulation by Martial, Aiguier, and Guillaume Carlier. You have, so quite related to the Barycenter problem, the matching for teams problem. So now you have that your mu I represent different teams. And in economics, so you want to match individual from each team such that you maximize, because you are it's an economic problem, you maximize, let's say, the happiness of each individual, where happiness means that everyone wants to earn as much as possible money. And then you have this very nice application to density functional theory, where your optimal plan returns you the probability of finding electrons in x1, x2, xn, such that you minimize the electron-electron repulsion. And this was introduced by these two teams, the Italian and the German one. And I think that Paola is here today. So even so, if I say something wrong, she can correct me quite easily. And then I think that it's some sense related to the previous talk. You have this nice, very nice application to uncompressible Euler equation, which was introduced by Jan even before his quite more famous theorem on the quadratic cost. And so now P gives you the mass of fluid which is following a path omega. And we do numerics with Jean-David and Guillaume some years ago. So this is here where was my golden age as a mathematician. And then you have following the idea. Yeah, I got old quite fast. And then you have another nice application to mean field games and etc. So just I want just to focus now on this application to density functional theory. So I do not repeat all the usual story about it, but the main idea is that now you want to minimize the electron-electron repulsion. So first of all, the electrons now are indistinguishable. So it means that instead of having n different marginals, you have n marginals, and they are all equal to this rho, which is the electron density. Moreover, from now on, so for me, the total mass of rho will be equal to capital N, where capital N is the number of electrons in your atom or your molecule. So of course, if if this makes you having some nightmares, I mean, of course, you can rescale your problem by a factor 1/n, and you obtain exactly the same energy as having a probability measure. Okay. Well, let's say that we can call this as repulsive optimal transport, because now the idea is that you have this particle and they want to be as far as much from each other, of course. And you have, of course, the constraint that of the density, so you cannot have particles going to infinity to solve your problem. So you have the Coulomb cost, then a slightly less repulsive cost, which is the harmonic one. So it's just see the Gambo switch cost, so the quadratic cost, but with a minus. So just to be repulsive. Then you have this determinant minus the determinant, and this one was introduced by always Guillaume Carlier. So it's our local star of optical transport, and Bruno Nazaré, I think in 2007 or something like this. So the idea is that you have this point x1, xn, and you want to find the polytope having this point as vertices, which has got the maximum volume. And so you minimize minus the determinant of the matrix that you which has x1, xn as column. And then you have this cost, which is h, composed with the sum of x1, xn, where h is strictly convex. And if you remember it, is actually the example that I made some minutes ago. So x1 plus blah, 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 n modulus square. Okay, and so why this cost is important? So let me do this this example, because then we will see that everything will be different in the grand canonical case. So just take this repulsive harmonic cost. You can develop the square, and then what you find is that you can rewrite it as an h, which now is this modulus square, minus the sum of xi squared. So assume that now rho has a finite second moment and compute the energy of these two costs. What you find is that the energy of the repulsive one is just the energy of h minus the second moment. But if now the second moment is constant, your marginal has a finite second moment, this does not contribute almost anything to the optimization problem, and you just are optimizing the same problem. So you just can study the problem with H to have all the information you want on the problem with the repulsive harmonica. And especially you can characterize the optimal plan, because you know that a plan is optimal if it's concentrated on an hyperplane. And so, which is this hyperplane equal to k, where k is just the sum of the barycenter of the first moment of your marginals. And so what we did is actually using all the information we have on H to deduce that the uniqueness for the repulsive harmonic uniqueness may fail, and you have this fractal solution. So I do this example because then you will see that in the grand canonical case, this nice thing won't work at all. Moreover, I mean, we will, with the repulsive harmonic, we will be in the worst possible case for the grand canonical having a solution, having a minimizer. Okay, so if there are no questions, it's time to go to this grand canonical stuff. So the idea is the following one. The main idea. So, for example, you are in Paris, okay? So you know that you have all the bicycle in Paris, and you know actually the distribution of this particle of these n bicycles in Paris. But now you are not interested in knowing this p, but you want to know what happened in just an arrondissement of Paris. So, for example, I took in this case the 14th because it's where I live. So you see that if you want, you can track me because you can stalk me because I obviously forgot to get rid of my house. And now you want to see what happens, but unfortunately, you have that. Around each arrondissement exchange bicycle with Paris. So you do not know exactly how many particles are in the 14th. And so you start to build this grand canonical, this vector. So this is actually the probability of having 0 bicycle. And then you start, okay, what happens if I have 1, 2, till, of course, in this case, capital N, because you cannot have more than the total bicycle in Paris. And so you build this vector of measure. So Pn and then let's say 0. Okay, maybe an abuse of notation. And this actually is a grand canonical. So what's happening? Each time you try to localize something, so to localize your n probability measure, what you obtain is actually a grand canonical probability. A grand canonical probability. So now the idea is that okay, we do not have usually this p, but okay, we do not have this p. And we have to define in a nice way grand canonical probability measure, and then of course an optimal transport problem. And now why we actually want to do this? So I just come back here because I have some blank space. So the idea is that now you have a large molecules, okay, with a number of particle n, which is huge. So usually when you do simulation, you are happy when you have when you manage to do 4 or 5 marginals simulation. Then you go to talk with Paula and you feel like a loser because in chemistry they actually need to run simulation with this n, which is huge. But actually you can see that this problem the computational complexity actually grows like an exponential in the number of marginals. So it means that at a certain point when n is huge, you have a problem actually to store your solution P even. So there are nowadays there are some nice relaxation from from Virginie Erlaché. She did some nice stuff on marginal relaxed problem with marginal constraint. Then there is this nice work by Gero Frieseke and Daniela Vogler on Monge state, where they actually can relax the multi-marginal optimal transport and solve in some sense the problem. But still there are some relaxation. And so what we want to do now, the question that we ask ourselves is the following one. Okay, we give up solving numerically this problem because n is too huge. And the idea is that, okay, let's try to think what happens if, for example, I start to decompose my molecules. And then I see I just solve my problem instead of on the whole molecules on each region I decompose my molecules into. And so you see that now what you have to do is localizing the optimal transport. And as I said, when you localize, you obtain a grand canonical. And so the idea is now having our grand canonical problems, solve each problem on a region of your molecule. And then, of course, you sum the energy in some sense, you obtain an upper bound on the electron repulsion of your molecules. So let's start to introduce this grand canonical stuff. So first of all, now I'm free to use, for example, an average number of particles, and now this n. I mean, there is no need to be an integer anymore. Okay, it can be 2.5, 3.5, whatever you want. Of course, not 0. I mean, or not a negative number. And this actually gives you the average number of particles. Okay, in your system. And now we need to define the set where we are defining our problem. So let's start to define our grand canonical probability measure like this. So you have symmetric positive measure. Symmetric because of course all the marginals are equal. So you do not, I mean, you can restrict yourself already to symmetric stuff. And then P0, of course, is just a positive real number because it gives just the probability of having 0 particles in your system. And then you define as follows your probability, your grand canonical. So the grand canonical is a collection of non-negative measure such that the sum of Pn omega n. So each Pn omega n gives you the probability of having n particles and exactly n particles. And of course, the sum of this stuff must be equal to 1 because you want a kind of probability measure. And then you can compute the marginal of your grand canonical. And so you have just the 4 stuff, and then you sum n times the marginal of each Pn. Why n times? Because again, you have a symmetric measure. Okay, and then now what happens? P0 is actually a real number. Yeah, because I mean you do not have measure. I mean, it's just a real number, but it doesn't count, of course, when you compute the marginal. Okay. So any other question, definition of the grand canonical probability measure? So, and now what happens? So you give yourself the average distribution rho, and of course the sum, the mass of rho is the average number of particles in your omega. And then you are ready to define your minimization problem. So now you see that you are minimizing the sum of Cn dPn. Oops. I hope that, that I really hope that I won't receive any weird stuff during the talk. So you want to minimize your energy over the grand canonical ensemble, over the grand canonical probability measures, having rho as average measure. So it means that now you want to the constraint you impose is that the marginal of your grand canonical must coincide with the given rho, of course. So we are going, we can, going back soon on the hypothesis on Cn, but for example, if you take the case of a pairwise interaction, so like the Coulomb one, so just take C0, C1 equal to 0, because of course, if you just, I mean, it doesn't make sense having a 0 or one particle, a cost related to this. So here, okay, so here is a 2, of course. Then you know, you can prove quite easily that a minimizer for your problem exists, and moreover, this is actually quite important because usually you have to deal with functional having your grand canonical, your optimal transport problem, plus some congestion, some other functional depending on rho. So, and then you have this external minimization over rho. So you want to having some lower semi-continuity of your energy. And of course, in this case, we are able to prove that our grand canonical is actually lower semi-continuous for the tight convergence of measures. So of course, let's do some remarks. So first of all, so you are relaxing in some sense your multi-marginal problem, because I mean a convex relaxation of your for your previous problem. So what happens is that when you have that this number average number of marginal is an integer, okay, I still have time, right? Because you know that if you do not stop me, I can speak, I can talk for hours and hours. Oh, that's perfect. Not 31. So when you have this average number of particles, which is an integer, what you obtain is that the energy, the grand canonical energy, is of course smaller than the canonical one, because of course you are minimizing over a larger set. The existence actually still holds with a more general class of cost, but we have to ask these. So first of all, in order to have a well-defined minimization problem, you have to ask that your cost is stable, meaning that you have for all Cn you have these inequality. So in some sense, you have that each Cn is bounded from below by the number of this small n number of particles. So this is actually quite well known hypothesis in statistical mechanics. So the stability of your potential. And this actually gives you that the minimization problem is actually finite. And then in order to, but actually you can prove that even if your cost does not grow in some sense in a nice way with respect to n, actually you are not able to prove existence of minimizer. And so you have to add an extra hypothesis, which is known as a superstability. And superstability means that your Cn is blowing up quadratically with respect to n. So let's say that this guy is epsilon n square. Okay, and now that you have this, actually you can manage to control the minimizing the subsequence you extract from your minimizing sequence, and to prove that the limit actually has the right margin. It's a solution of your problem. But I mean, we didn't manage to get rid of these hypotheses in order to prove existence of minimizer. And of course, trivially, in the case of, for example, the Coulomb cost, this hypothesis is always satisfied. And so we are in some sense in a good shape. And then you can actually ask what happens if I look at the lower semi-continuum with respect with in duality with C0, and still you have to add this monotonicity hypothesis on your cost. But again, if each pairwise interaction is positive, then this is trivially respect. So again, respect is so satisfied. So again, with the Coulomb potential, you are in good shape to have all the nice property you want, and then you can just the sum, yeah. No.
But isn't this like the arbitrary choice? Does it come from physical consideration?
What?
It looks like you're comparing different ends, but it's like a bit chicken and egg, like combining it's normal position to compare two particle.
No, but I actually don't know how many particles are in my system. So I cannot, I mean, I cannot compare 2 or 3. I'm obliged to see what happens for all the particles from 0 to infinity. Of course, I mean. Okay, so I think that usually grand canonical, but there are physicists in the is usually done for in plasma or stuff like this. And of course, here we are using it in some sense to localize optimal transport.
But so there will be physical system for which a reasonable model would be that the moment of number of particles and you will minimize the sum of it.
Yeah, but I mean also in economics, if you think so, I usually think to this example that you are in Gare du Nord and in the morning, and you do not know exactly the number of people at a certain time in Gare du Nord, and so you just know an average number, an average total number of people during the day, and then you start to see how the distribution in the railway station. I mean, you just have these grand canonical stuff, which gives you the distribution if you have 0 people, one person, two people, and so on.
Yeah, but then you could decide normalization of the number of maybe that's
normal. I mean, you.
like one over n of the sun. Or...
Yeah.
There is somewhere one.
Yeah, the fact is that I mean it depends what you take here. So, for example, of course, I mean we are considering symmetrical, and so you have, if you want, you can take one over n before. I mean here, if you want to rescale your problem, but actually we. We are trying to hide everything in this grand canonical stuff. But at a certain point, I mean, I mean, when you prove stuff, at a certain point, you have, of course, a normalization factor that comes out from your sequence, and you have to deal with it. Okay, so I was here. I have another remark that, of course, now I'm considering just one marginal, but actually you can extend your problem also to the case of 2 average marginals. So you have row 1 and row 2. And maybe they do not have the same mass, and then you just have to take probabilities over omega times 1, 2. And what happens is that you, for example, at small n, you have this guy sigma 1. Of course, sigma can take values 1 or 2. That's x n sigma n. And what happens is that this Pn gives you how many agents and one of row 1 you are transporting onto n2 agents and 2 agents of row 2. So in some sense, you can do some unbalanced stuff with this guy, even if you are, of course, complicated a little bit things, because you are dealing with an infinite collection of measures. And so just on the literature side, just cite this truncated version proposed by quite, I mean, 2 years ago, I think, by Bouchité, Buttazzo, Champion, and Gigi De Pascale. So okay, there is a D missing, where actually in their case they fix the maximum number of particles of n that you can have, and then they let's say they have a sort of truncated grand canonical stuff. But what we can prove is actually, and this is nice, that we have a convergence of their problem 2 hours when this maximum number n goes to infinity. So now, of course, what one can think is that, okay, you are trying to do all this stuff in order to simplify computation, blah blah, but you are dealing with an infinite collection of measures, so you are not simplifying anything from the computational point of view. And the fact is that we have to work a little bit on the support of, let's say, of the grand canonical. And so what we can say is actually the following stuff. The grand canonical has a compact support if you actually can determine can have an interval of n and max, such that the only measure that stay alive, let's say, are the one such that small n is in this interval. And so you can a priori already say that all the you have probability 0 of having less than n mean particles or larger or great more than n max particles. And so what happens, for example, in 1D is that if you have let's say 3.5 on average, so you just have 2 particles or 3 particles to look at. And then you can do exactly the same thing where when the dimension is a little higher, and we have this bound, lower bound and upper bound on n, which are kind of complicated. But it means, for example, that if you have 3.5 on average particle on average, you just have to look at the probability of having 2 particles, 3 and 4, not more. So it means that you are reducing a lot the measure that you are that you must consider, for example, in your numerical examples. And so it means that if you have Coulomb and you just decompose your molecule or your domain in a subdomain where you will just have 3.5 particles, so you go from a problem with a huge n to solve okay, the end of the problem with 2, 3, and 4 particles in for marginal plans. So you reduce a lot the computation you have to do with respect also to the canonical case. And of course, in this very special case of n equal 2, you just have that the grand canonical is always canonical. I mean, this is not surprising. And just let me say that the way we managed to find this bound is again thanks to Lib, because there is this nice paper on maximum negative ionization of molecule and atoms, and we actually use this idea in order to find this bound, and then we refine them by another trick introduced by Rupert Frank in the paper always on ionization, I think. So again, you can derive, of course, a dual problem as in the classical case. So I try to speed up. You have now a potential associated to the constraint, and now this beta, which is a constant, and it's associated to the fact that you have a grand canonical probability measure. So the idea, so you can prove actually that strong duality holds with with the same hypothesis on the cost as the one to prove existence of minimizer. But then the problems arrive when you have to prove existence of such a potential. And the idea is that you look at the relaxed problem when instead of taking a phi bounded continuous, you just look at phi in L infinity. And if you have some additional hypotheses on your cost, you can prove that phi is actually locally Lipschitz on the support of your marginal rho. And if the support rho coincides with your omega, you have that your phi is Lipschitz on all your domain. So let's see some just this simulation. So we take the average rho, which is just the sum of 6 Dirac, and you have that the total number of the average number of particles in your 0, 1 cube is 3. And then you try to find some grand canonical configuration, and you see that if you put exactly your Dirac in this position, you just have as a grand canonical P2, so 0, P2, 0, P4, and 0. And what you 0, and what you have, okay, I'm saying that okay, this is an abuse of notation, let's say. And you have that P2 is concentrated on these 2 Dirac 2 points, 2 red points, and P4 is concentrated on this for 1, and you have the 1/2 probability of having 2 particles in your square, or to a 1/2 probability of having 4 particles in your square. And then you can start to perturb, for example, to do perturbation of this point, and to see the region where you still are grand canonical, so still you have a P2 and P4, and you discover that you have this small region in your cube where you stay grand canonical, and once your P is out, your point is outside this region, then you become immediately canonical, and so you have that all is concentrating on P3. So it's actually a very small region in all your square 0, 0, 1. And just to see what happens when you have this harmonic cost. So of course now the problem is that this n square comes to account in your optimization problem, because you do not have here the average marginal of your grand canonical, so you have to leave it, and so you cannot compare what happens with the H cost, the H potential, or the repulsive harmonic potential. But maybe the worst is that when you have the repulsive harmonic cost, actually this happens. And so this is actually quite bad with, in comparison with the canonical stuff. And so let me finish by talking about Schrödinger in the grand canonical ensemble. Okay, there are also notifications from Netflix, and I hope that it's so. You can define again some sense in the same way your Schrödinger grand canonical problem. So let's consider this Gaussian state, or Poisson state. Poisson state. Okay, there is always a debate between Mathieu and me about it, but okay, so let's say that Robert Mecan was right. So Poisson, your Poisson state, grand canonical state, and then you can define your grand canonical at positive temperature as in the classical way. So by adding this relative entropy, and if you develop this relative entropy, you discover that this is actually equal to minus the entropy of P, and plus some constant which just depend on rho, so typically is rho log rho again, so it's the entropy of your marginal, and this SP, and now you see a factor n appears, is P log n factorial P, so it's sum of n Pn, so it's the n factorial, which is the Boltzmann factor, in order to have the right definition of the entropy. This is actually because we are not if we want to do things in the right way, we should take omega and mod omega with all the permutation, because of course all your particles are indistinguishable. And so there is a way to get rid of this n factorial. And so what you can prove is that your entropic problem now has a unique minimizer. And moreover, you can just have a Cn which is stable. You do not need any extra hypothesis like the superstability. So this because you are adding the entropy, which gives you a better control of your minimizing sequence. Of course, you can prove that when the temperature goes to 0, you retrieve your grand canonical problem with this extra constraint that the entropy mass, the relative entropy with respect to your Poisson Gaussian state must be finite. And then you can see what happens when the temperature goes to infinity, and what you find is your energy evaluated the Gaussian of the Poisson and your reference state. So again, you can write down duality as you usually do with the canonical stuff. So you have again your potential phi, and so here you recognize exactly the dual problem. If you just have if you do not have a grand canonical, you just retrieve the classical entropic multi-marginal problem. And you can prove again the existence of optimal potential, and again we use an argument by Lib by Lib. And what happens is that of course, given the optimal phi, you can retrieve this Gibbs state, which gives you a solution to your primal problem. So I think that all the n factorial n are to the right, in the right place. And okay, you can run some simulation. And what happens, for example, in 1D, we take actually something nice. So just the uniform measure on 0, 1, and an average number of particles to 2.5. And so what we expect is just having P2 and P3. And so I run this simulation just to be sure. So with P0, P1, so you cannot see it, but I actually write till P. Okay, I think that in the picture here I put just P4, but if I remember, I do with P0, P6. And so what happens is that you just have, so if you look here, the row associated to, so maybe I can zoom, the row associated to P1 and to P4 are actually equal to 0. It means that you are not putting any mass on, there is no probability of having 1 particles or 4 particles, but you just have 2 particles or 3 particles. And this is the support of the pair density. So with P2 is, of course, this one, but with P3, of course, you project your free marginal onto the double, I mean, to the pair density associated to 2. So it's just a marginal of P3, and then you you plot the support. And nice thing is see that your grand canonical, just your P2 and P3 are actually supporting, going to concentrate on some structure which are quite similar to the Monge map that you have in the classical case. So there are a lot of work that is that must be done. Must still be done, especially so is that there is for example a nice way to decompose your molecules. So there is a nice work by Eric Cancès Andreas Savan on it, but we still do not have done for now any kind of simulation to see if this is going in the right way, and especially what happens if we decompose our molecules. So we have a bound on an energy, we are doing it in the right way, so we think so, but still we have to do this. But in a couple of weeks you will enjoy reading this almost 80 pages paper on this stuff that I tried to sum up today. So thank you. Ah, okay.
Oops.
Oh, that's fine.
Thank you, Luca. So I see here that Guy Bouchité has some questions. So Guy, if you can just unmute yourself if you want.
Yeah, I try.
Yeah, it's working.
Bonjour,
We hear
je ne sais
you.
pas si vous m'entendez.
Yeah.
Bon, ben, bonjour, merci pour l'exposé. J'avais une question concernant l'histoire.
Sorry, can you speak English maybe, because there's many people on here.
I have a question concerning the size of the support of the grand canonical measure.
Yeah.
You mentioned for in dimension 1 the gap between the maximal one and n minus and n max is equal to 1.
Yeah.
And you give a bound of the gap, that means the difference between n max and n min in terms of n, but it doesn't depend on the dimension d in that case.
In one dimension is usually a special case, you know, because
sure.
you use. I mean, we use the fact that R is ordered, and I mean the same trick that you use for usual optimal transport. We do it. We use it to find this window, this small window on the support of your T.
Yeah.
And yeah.
But the bound you have doesn't depend on the dimension d. And
no.
if I understand, the gap may blows up like a square root of n, something like that.
You mean in
The difference between n max and n minus, n min, looks like a square root of n. No? That is the square root of the number of particles.
Yeah,
Okay.
of course, yeah.
Okay. Do you have an example where even the gap is strictly greater than 1?
For now, no. So I mean, we think that actually we can one can improve this bound. I mean, I'm not sure at all that there is a sharp bound on your window.
Okay.
So because we had this example. So for example, this one where actually we are stuck with T2 and T4. So you just have this small window. Whereas maybe you, I mean, if you apply our and I think that we try also with some more Diracs, and still we are in this small window. So I think that we can improve this bound, but we do not find.
Now the problem is to know if it can be greater than 1 or not.
Yes. So
even with a discrete measure, is it possible or not? Because
yes. So this.
Okay.
This is an open question.
Because there was several issues which are linked to the ionization phenomenon.
Yeah.
And you relate a paper, I don't know about that. I would like to know this kind of technique to obtain the bounds. And it is very interesting issue, I think, because there are a lot of consequences which come from
and so moreover, you have this bound for the column cost, but for example, if you have the Ritz one, so just 1 over modulus to the power s, the window is actually no. I think that this still can work because no. Doesn't. I mean, the bounce is the window is actually a little larger because we cannot use the stuff from Frank and Nam to improve the bound.
From whom? From Frank?
Rupert Frank and Nam. But I mean, if you write me an email to remind me, I can send you references.
Okay, I don't know this paper. Okay. Thank you very much.
We had Emric also. Please go ahead, Emric.
Yes, thank you. You hear me?
Yeah.
So, as far as I understand, so all these problems, you could consider them as optimization problem on the set of probability measures on the set of point clouds of empirical measures, and the entropy that you define at the end in this case would really be like the relative entropy with respect to the random Poisson point clouds, something like this, right?
Yeah.
That's actually quite interesting. I wanted to mention because I hadn't realized, but yesterday I didn't talk about it. But in our branching problems, actually, this kind of optimization problems is exactly what you need to solve at the initial time.
Yeah, indeed. When you talked yesterday about your problem, I start thinking about the fact that you have something like this grand canonical stuff happening.
Yes, we do actually, and yeah, already in the case when you have only the entropy. So in the Poisson case, it's okay, but as soon as you have more complicated things, as far as we could find, I mean, we don't have any existence result actually.
So actually, all the existence results that we have. So there is these. So of course, without the potential terms, so without this guy, but with just the entropy, is this paper from the 80s of Lib, where he gives most of the result on it. So actually, when you start reading Lib's literature, you find out that he solves many of the problems as you. So, but I mean, if you want, I can send you also the paper of Lib about this stuff.
Yes, thank you very much.
Thank you, Emric. And then we have a question by Dirk.
Thank you very much for the nice talk. I have a question about the entropic regularization. So when you add temperature, if you don't mind. So I would have expected it to kind of move out also in the number of particles, but you show that it still kind of localizes for 2, 3 instead of spreading out.
Yeah.
If you raise temperature, does it then spread out or does it stay kind of localized?
No, I mean, it just spread out the localized plan. So each P2, P3, but it doesn't spread out, let's say, the support of your collection of probability. I mean, it's in some sense it's disconnected. There are two disconnected steps. So if you want, you can look at what happens at the local level of your grand canonical. So at each measure Pn, and so the entropy actually affects this Pn, but it doesn't affect the let's say the general structure of your grand canonical. So you do not have you still stay localized on P2 and P3.
Okay, that's very surprising. Thanks.
And perhaps one last question from Paula.
Yes, thanks, Luca, for a very nice talk. So my question it's on the bounds for dimension larger than 1. So for 1 dimension, your bound is what we always expect.
Yeah. I forgot to cite you.
No, don't worry. No, I mean, for d = 1, the bound it's what people always have, let's say, in DST. But the one for d larger equal than 2. So, I mean, do you have examples in which your n min and n max are in fact spread more than, let's say, the 2 closest integers? Because you have a larger support, right?
So we do not have an example, and so this is why I believe we can improve these.
Okay, this was my question.
These bounds, but actually, with I mean, at least with the tools that we know, I mean, we do not manage to improve them. Maybe, I mean, we are certainly missing something in the proof. But
so you did try to find examples in which you would spread out beyond the usual closest integers. Okay, but you didn't find. Okay, that's interesting.
Yeah, for now. I mean, so this actually was this example. So when we try to when we put ourselves in this 0-1 and we start to find all possible combination of Dirac in order to see if we manage to find, for example, a P5 or a P6, but we do not. Okay, this is not actually the case because with 3 you just have 2, 3, or 4 and not more. But I mean, we tried with I think 4 and we didn't manage to find something more than P5. But we always stay P3, P4, P5. So this is actually why I believe that these bounds are not totally sharp. Let's say that they are sharp up to our knowledge and all the tools that we use.
Okay, very nice. And just quickly going back to the question of Dirk, can you explain in an intuitive way why in the entropic, even if you raise the temperature, you remain localized with respect to n, with that you don't spread to larger number of particles?
So I think so. My intuition is that even you are so it's actually in the how you are defining your entropy. So still the average this h actually is this. Is the sum over your n of your what Pn log log Pn over G rho n. So I mean, if you look at it, actually you are just adding entropy only to your Cn. So you are affecting directly just your Pn, but in some sense you are not doing anything on the support of your grand canonical in general. So you're just acting, you are just regularizing the support of each Pn to me.
Yeah.
So in some sense, is a very local regularization of your grand canonical, and not something that is regularizing in general your grand canonical.
Yeah, because you're, okay, no, it's clear. It's very different than the idea one has in physics. You raise the temperature. Yeah. Okay, yes. Okay, thanks a lot. It was very nice.
Okay. Okay, so I think we have to stop here because we need time to go lunch. So thank you again, Luca. Nice talk. And for everybody out there, so we will resume at 2 p.m. Lisbon time, so 3 p.m. for the rest of the world. Thank you. Yes, well.